right. In that case, I'll dive into sensitivity analysis. In this workshop, we will talk about two types of sensitivity analysis: deterministic and stochastic, or so-called probabilistic. The stochastic is maybe somewhat more complicated, and we will talk about it on Thursday, if I recall. So for today, we will just stick to the deterministic sensitivity analysis, which will illustrate the concept, and hopefully then make explanation of the stochastic sensitivity analysis a little bit better. But before I start talking about sensitivity analysis, I would like to talk briefly about uncertainty. In health economics models, there are, well, I have 4 bullet points here, but there are 3 main sources of uncertainty. It's stochastic uncertainty. That means that even if everyone in this room has the same probability of getting the flu or whatever outcome we're interested in, some of us will ultimately get the outcome and some won't. And if we were to run this experiment in a different universe, maybe different people would get the outcome and others won't. And that is something that, that's uncertain, and so that's what we call stochastic uncertainty. That is something that this uncertainty can be taken into account using a so-called microsimulation, which is again something that we will talk about on Thursday, so I will skip that. Parameter uncertainty is what I already briefly talked about. The fact that you found in the literature that the chances of getting the flu is 25% within a year. How certain are you that this number is actually true? It was likely estimated based on a sample, so there is some sampling variation. A different sample could have resulted in a different number. When you think about costs, hospitalization doesn't always cost 25,000 rupees. Some people will have more complicated hospitalizations. Some won't. Some will be pretty easy and stay for a day or 2. And maybe like that estimate, 25,000, maybe maybe that's an average, but again, it's an average based on some sample. Maybe a different sample would lead to a different distribution of inpatient costs. So this uncertainty in the values of the parameters that come in the model, that is what we assess, like the impact of this uncertainty is what we assess using a sensitivity analysis. That's what I'm going to talk about in this presentation. There's also structural uncertainty, which is it's the uncertainty stemming from the way you set up the model. In our example, we had 3 terminal states: healthy, flu in the outpatient setting, and flu in the inpatient setting. But as many of you suggested and saw, that was a huge simplification. And maybe if I set up the model differently, maybe it would lead to a different conclusion. So there is uncertainty stemming from the way how I or you will ultimately set up your models. The structural uncertainty is very difficult to deal with. There is really no simple method to assess for it. You just have to do your best. And in the manuscript that you will ultimately write, you have to explain and justify why you set up the model the way you did. That convince people that the uncertainty stemming from the structure of the model is minimal. There will always be some. You will never get rid of it, but at least you can minimize it. everyone responds to things differently. People have different risks of getting sick, getting healthy. So that's just that's a factor that comes to, like ultimately in the analysis you will get an ICER. It's one number, but that doesn't mean that that applies to every single one of us. Even if we knew that the model was set up correctly, even though we knew that all parameters are correct and exactly set at the value that is true, there is variation across people. But that's just something to keep in mind. I will not talk much about that. Stochastic uncertainty is when the parameters are fixed. So let's say the probability of getting the flu, it's 25%, but the ultimate outcome will be yes or no. It will not be anything in between. It will be yes or no. So that's stochastic uncertainty. Whether based on the fixed rate, fixed probability, you will acquire flu or not. Heterogeneity is that your probability of getting the flu may be different than mine, and may be different from, like all of us. And every single one of us have their own probability of getting the flu, based on our personal histories, genetic bond, and so on.
So would it be right to say significant variability, whereas that is related to the probability of?
Yes. Yeah. Right. So now, from now on, I'll talk only about the how to account for parameter uncertainty. So because we know that, or we don't know the true value of parameters, we only have estimates. And if the estimate is not precise, if we have an estimate that's slightly biased from the true value, if we were to implement, for example, this vaccination program, and we would find, our model would tell us that the vaccination program is cost effective, then we implemented it. It's actually not, because the underlying probabilities were wrong. We can account for this by varying every single parameter in the model over some range to assess how the ICER, the ultimate outcome that we're interested in, how it varies with different values of the input parameters. Let me stress here that doing a sensitivity analysis is absolutely critical. If you read a study that just shows you one number, one ICER, and that's it, that's not a good study. There's parameter uncertainty in pretty much every single cost-effectiveness study that has been ever published. And a good analysis should admit that and do a sensitivity analysis to show how robust, how reliable the model is, the model outcome is. In general, for sensitivity analysis, we distinguish between one-way, two-way, and multi-way sensitivity analysis. Can you guess what it means? Well, it's on the slide, right? It's pretty straightforward. I'll ask a different question in a second. So one-way sensitivity analysis means that of all the parameters, in the vaccination we had probability of getting the flu, effectiveness of the vaccine, probability of being hospitalized, we had cost parameters, we had utility parameters. One-way sensitivity analysis would mean that we would vary one parameter at a time, keeping everything else constant. And we would look how the ICER, the ultimate result, how it varies with changes in every single one of these parameters. Two-way it's obvious you just vary two parameters at once. Maybe you would vary the probability of getting the flu and the effectiveness of the vaccine. Multi-way, you just vary many parameters at the same time. Do you think it makes like one of these three? Well, I also added the probabilistic, but we will talk about that later. My question is, do you think that one of these types of sensitivity analysis is better than other? And if yes, then why?
Practically, the real world parameters sensitivity analysis might be better. The real world scenario parameters keep on changing. Practically, that may be better. And then we can change our decisions depending on what parameters we need to focus on.
Which parameter is most reliable? MultiWay would rather give us a more real world, so we cannot predict.
How possible combinations are present?
In the multi-way, you get all possible combinations of all different values, right?
But then one way probably is change one CP, change the CP. So and then see what is effective and then go on for multiple. So that would probably flow through others.
I think we're getting exactly to what I tried to say. Is they all have value, and you use them for different kinds of things. If you want to find out what is the one single parameter that influences your result the most, then you would do a one-way sensitivity analysis on every single parameter separately, and you would see that maybe, like the effectiveness of the vaccine doesn't really matter as long as it's within some reasonable range. Or maybe you would find that it matters a lot, and that the cost of the vaccine doesn't really matter, or that the qualities don't. It doesn't matter if it's 0.85 or 0.8 or 0.9. So one-way sensitivity analysis is really good in finding, the one parameter, or maybe two or three, but essentially single out the parameters that influence the results the most. On the other hand, the multi-way, which two-way is essentially a subset of the multi-way sensitivity analysis, gives you a better idea of what can happen in the real world. Because in real world, things change, and they don't wait. The one thing doesn't change, and one thing changes and everything waits. That's not how it works. In reality, many parameters can have different values. So the multi-way sensitivity analysis gives us a better picture of what can happen in the real world, but the one-way gives us a better sense of what parameters are the ones that drive the result. So over what ranges should you vary the parameters? It depends. Usually you would go, if you have, for example, if you find an estimate of your parameter of interest in the literature, there may be some measure of variation associated with it. You will have either a standard deviation, you can have 95% confidence interval. So those would be good ranges to vary the parameter. From the lowest point in the 95% confidence interval to the highest point. If you have standard deviations, you can do plus minus 1 to maybe 3 standard deviations. 3 seems a little too much. If you don't have this guidance, clinically meaningful values are always good candidates for like the minimum, the lower and upper bounds for sensitivity analysis. But always make sure that you vary the parameters over a plausible range. The probability cannot be below 0 and it cannot be above 100%. So, for example, if you had an estimate, a point estimate and a standard deviation, and somehow 2 standard deviations would get you out of that range, just don't do that. Just make sure that you stay within a plausible range. Like age, for example, can be a parameter in your model that cannot be negative. Probably like above 120 should not make much sense. So it always depends on the particular parameter in question, like what makes sense. When I talked about the expert opinion, essentially getting the parameter from an expert, that is certainly, if there is no literature and you have no other way to obtain data, an expert opinion is much better than just like throwing a dart on a wall. It will get you at least to some like reasonable location of the true parameter. However, it's just like an opinion, right? It's still an opinion. So those parameters really should be subject to a thorough sensitivity analysis. Those perhaps, for example, like if our expert told us that the probability of getting the flu is 25%, maybe we should vary that parameter from 0 to 100%. We would cover all possible values of that particular parameter. Yeah, so maybe I should briefly talk, I don't really have this on the slides, like how to present the results of a sensitivity analysis. In a one-way sensitivity analysis, you really can show perhaps the lowest value of the ICER and the highest value of the ICER for all possible values you used for that one particular parameter. When you get to two-way and multi-way sensitivity analysis, things get tricky. A two-way sensitivity analysis can be presented as essentially a two-dimensional table. Each dimension would present values, plausible values of the two parameters. And in that table, you would, for each combination, you would show the ICER. But once we get to 3 dimensions, that's a little tricky to present, but still doable. 4 dimensions, that's pretty difficult. So in that case, you would probably stick to you would record the lowest and highest value of the ICER. But as we will talk later, this type of analysis is usually actually done not in this deterministic way, means that you just decide, okay, so let's not try 25%, let's try 20% for the probability of getting the flu. Or let's try 10%. You just decide whatever value you want to try out, if it works, and how it changes the result. But usually the multi-way sensitivity analysis is done in the probabilistic or stochastic kind of way. And I will show you how the results look for that analysis later when we actually talk about stochastic sensitivity analysis. Now, interpretation. So let's say you first run the analysis in the so-called base case scenario, which means that you will use all the point estimates for every single parameter. You get some ICER, you compare it to your willingness to pay threshold and decide well, this intervention is cost effective compared to the alternative or not. The purpose of the sensitivity analysis is to show that if you vary the parameters, will the conclusion change? If you find that no matter how much you vary all the parameters in the model, you still find that providing vaccine to elderly patients is cost effective, then you can be damn sure that this is a good intervention. In most cases, you will not find that. You will find that in this particular combination of parameters, it's not cost effective. It's too expensive for the incremental benefit. Maybe in some combinations of parameters, you'll find that it's actually cost saving. That providing vaccine, even though it costs money, it's a good investment because people will not get sick and we will not have to pay for their healthcare. So then you can describe what are the chances that the intervention will be cost effective, cost saving, or not cost effective. But in general, it just gives you a sense how confident you are in your recommendation. If you find that even the slightest change in some of the parameters can totally change the conclusion, then as a policymaker or the decision maker, I wouldn't trust that analysis. I would trust the analysis, but I wouldn't make decision based on it. And that's pretty much all I have for a deterministic sensitivity analysis. And so how are we doing? So we now have 1 more hour.